Hello everyone, welcome to PyCon 2020, the PyCon Sweden edition. Today we are happy to have Misbah to talk about production-ready machine learning pipelines in H&M. And Misbah is a machine learning engineer and competence lead at H&M and has been working on the next generation MLOps platform for H&M. Let's welcome Misbah to have the presentation and the talk.
Thank you, Edwin. Hello, everyone. I'm a avid PyCon fan. It's been a bit rough year for PyCon that we cannot see the community in person. However, I'm happy that at least we are trying to make the best use of it. But let's come to our key discussion area. This talk is about H&M and it's about machine learning, but ultimately it's about how we are trying to make best decisions that helps our hundreds of millions of customers using technology. So let's get started. So this is the agenda for today. We're going to talk about why do we need a scalable machine learning platform? And then we are going to talk about what kind of building blocks do we need to achieve that. And then we will share some details about how we try to implement that and what are our next steps. Now, those of you who have not heard about H&M, it is one of the largest clothing retail that brings fast fashion to hundreds of millions of customers all over the world. Its journey started in 1947, so it's a 70 plus years old company. And it managed to scale and thrive in different periods of time and has become a very well-known brand all over the world. And our current footprint goes 5,000 stores in 70 plus countries and e-commerce in 50 plus countries. And we are quite a lot of people who are enabling all of it. The funny thing is that none of us makes any garments. So you can think about what all these people do. So we engage in designing, ordering, distributing, marketing, and selling garments. And that means the scale that we have, all these people that these control decisions that they make, the impact of it is huge. However, earlier this decade, we observed that we are slowing down compared to many other players in the market. And it's not because that they are we are producing something bad. It's because we were a bit too slow in adopting technology, in digitalization, adopting data-driven decision making. And we recognize our mistakes and we pivoted. Now we have taken steps to increase our e-commerce footprint, but we have also taken steps to embrace machine learning, artificial intelligence, and other algorithm-driven decision making. But ultimately, our goal is to be as much as customer-oriented as possible, meaning that we want to understand our customer to the fullest extent of our knowledge, and then we want to maintain a sustainable business. We have a 70-year run. We want to keep doing this for hundreds of years more. And then ultimately, we see being digital is the way to go. And we have taken significant steps in being more digital, but there are still some ways to go. And then we are adopting more and more data-driven decision making. Now, to give you an idea, where do we work is that we basically work with clothing and apparels for a lot of people in the world, but it can be organized into these 5 segments that you see in this slide. First, we design garments, and then we order garments. Then once the ordering is done, then we focus on how this garment is produced in the best way possible. Once this is produced and it is packaged, we focus on how to distribute this efficiently all over the world. And once it is distributed to the right channel, let's say store and the e-commerce stores, physical and e-commerce stores, then we focus on how to market these garments to our customers. And ultimately, what we also focus on, what is the best sales experience that we can give to our customers. Pricing is a big part of that. Now, what we have done is that we have launched many different projects in all these areas. For example, in design and buying, we have projects about identifying the demand, which garment, what is the demand of each type of garment. In logistics, we are figuring out how to distribute the garments in the right channel, in the right volume. In marketing, we are focusing on like what type of garment are liked by certain niche customer segments. And in sales, we are looking into markdowns, discounts, like what is the best discount prices to provide so that our customers feel that this is the best way to go. But we are not just spinning up these projects. As soon as we see that there are some common components in these projects, we also focus on building engines that can serve multiple projects. And therefore, we have demand forecast engine, we have order orchestration engine, we have intent engine and return forecast engines. But all of these engines, they are basically codes. No? So we are focusing on writing common libraries and then harnessing those across multiple engines. We are also sharing more and creating our platform for knowledge, where we write down our best practices and then we try to update them as much as possible. Also, when we see there is enough demand, we take away these common pieces and then we manage them as a hosted service. And then all of these run through on top of some kind of different types of data sources. We have data lakes, but we have other data aggregators and databases. And we are a total cloud-only organization, meaning that all our services run on top of public cloud. Now, all these projects that I have shown you, the way we work with them is almost like a startup. So it's a VC style ways of working. So anywhere we see we need to solve a problem, we start small. We write a proof of concept. We test the feasibility of the idea. Once we see that the idea works, then we take it to the pilot. We test it on a market, and then and see how the performance is, how complicated the solution is. Do we need to update the solution? Do we need to use more data? But once we have answered those questions, then we take it to industrialization, meaning that we take it in production to serve in decision making to multiple markets. And once we see that we are okay with serving with multiple markets, then we take it to the scale, meaning that we want to make it, we want to expand this use case or project to the global scale. Now, I hope I managed to explain why we are looking at scale. So if we are talking about scaling projects that comes from, let's say, that's come from industrialization to globe scale, we need to think big. We need to run. We need to support. We need an infrastructure that can support very huge scale ML pipelines. Right. But before we go into the details about how we design our architecture, let's look at some of the principles that we follow. Our first principle is that we want to separate the concerns. We don't want to pack our technology into one block. We want to keep application, storage, compute separate, so that we can change any pieces whenever we want to, and we can reuse the pieces as much as we want to. We also want to keep it stateless, meaning that any change in the system should not break other system. So you can start from anywhere, you can stop in anywhere. And then we want to be totally cloud native. We are application developers ultimately. We don't want to maintain our own hardware. We want to focus on application code as much as possible. Then we want to automate as much as possible. I mean, we still have a human in the loop, but we see the role of the human is basically business experts. So we have either data experts or business experts that should be part in the loop, and the tooling should basically support them to make their work as fast as possible. And then some key way we design our ML solution is that we always keep the scalability in mind. Like, we understand that all of a sudden our number of runs can increase from few tens to thousands. It can happen like that. But that doesn't mean that the rigor in our work should go away. We want to make our runs reproducible. We should be able to reproduce it, no matter it's 6 months old or 1 year old. And then, but that doesn't mean that we become frivolous. We want to minimize our costs as much as possible. We want to get the best value at the lowest cost possible. And we want to do it in an organizational friendly way. Ultimately, it's the tool and the machines, they support the humans, and therefore we need to build it in such a way that it supports the human in the best way possible. So that influences a lot which technology that we go for. So let's look at the different aspects of the work that we do. So normally in machine learning, the first stage of working is model exploration. You look at the data, you come up with some features. We basically use live data or much more realistic data. And then we implement different ML pipelines, training pipeline, serving pipeline. And then we also put in the different type of system testing, unit testing, algorithm testing. And once we have that, we also enable CI pipeline. That means iterating over the algorithm becomes faster. But once we have that, we focus on the actual aspect of running machine learning jobs. So first part is model training. And to do that, what we do is that we build model, we tune hyperparameters, we cross-validate the model, we also track model artifacts. Then, of course, we try many different variation of the model for some target, and then we need to choose a good model. And therefore, we go through the model selection process where we compare the model, we test the model on some kind of a benchmark, and then we transition the model to testing to production. Once a model is in production, it is a chosen model. Then we focus more on model prediction. And primarily, we have focused on batch prediction. The streaming prediction or online predictions, we are really new in that area. But these cases that I'm presenting is on the batch type jobs. But so what we do is that we run batch prediction, we output the result, and then from time to time, if we see that there is a divergence of the model, we do a rolling upgrade of the model serving. Finally, because we are on production most of the time in the year, meaning that we provide data-driven decision making throughout the year, we always perform we monitor model performance, and then we also monitor service performance. Now, let's go a little bit deeper into what inspires us to design the ML pipeline architecture. So these are like a high-level overview of machine learning pipelines that we use, and we mainly focused on model development and model application. So first, we have data-related components, like we collect the data, we clean the data, we create the feature. Then we have more machine learning algorithm related components, like we do model training and hyperparameter tuning. And then for the case of model application, this would be running different types of simulation. And then so that we tackle with many different aspects of the decision making. And then we also choose one holistic solution that works. And in both cases, the final stage is producing some reports that basically shows the quality of the model. In model development phase, this basically means looking at error metrics like mean squared error or median absolute error or other well-known metrics. For model application, these metrics change. Then we look into business related metrics. Are we reducing the stock that we want to? Are we increasing the sale that we want to, for example? Now, in terms of what are the best infrastructure to support these different types of jobs, we observe that there is no one execution environment that can rule them all. The main reason is that the nature of these tasks are different. So, for example, for data related jobs, they are embarrassingly parallel. So you can probably apply the same operation in each row, but there are like millions or hundreds of millions of rows to deal with. So this is easy to parallelize, but at the same time, it is quite memory intensive. On the other hand, model training and optimization, this type of work is more iterative. There are parallel algorithms, but there are quite a lot of algorithms like gradient boosting algorithms or linear optimization or hyperparameter tuning. Some variants of those, and especially we use those variants, they are quite iterative and they are very CPU intensive, but they can be memory intensive too. But the last stages, then we rely on visualization heavy workloads, and they are often not carried out in the local execution environment, but rather in a managed centralized platform. And therefore, the requirement is basically communicating high amount of data to those external platforms. So we see that in the first cases, for data intensive jobs, it's mostly about either you use like a platform like Spark that is good for big data processing, but there are some usages of native Python programs. In the second case, we exploit a lot on the rich library that community provided us, including TensorFlow, Keras, sklearn, and different type of optimization libraries. And in the last case, everyone knows about Matplotlib and Seaborn, but we also use Power BI, Tableau, these type of a more richer visualization platforms. Now, what type of execution environment would support these pipelines? So for the first case, for the data preparation, data related task, we see that an environment where you can run Spark jobs would be the best option. For the second case, you want a native Linux environment, but preferably in a big compute resource environment to run this job. In the last case, for visualization, you don't need a big machine. You just need a small machine to, interact with the external platforms. Um, and to iterate again, like we don't want to manage the infrastructure if we really don't have to, and therefore we have opted for platforms that allowed us to do that as much as possible. And therefore, instead of managing the Spark clusters ourselves, we focus on we opted for a managed Spark services like what Databricks would provide. For the second cases, we use Azure services, Azure virtual machine services, like having big virtual machines where we can run these compute jobs. And for the last case, we also use something like those. But we see that there is a lot of value instead of running things natively on virtual machines. There is a lot of value running things in Docker environment. That way you can share the same virtual machine to run multiple applications. Um, but we'll talk more about that later. Now, something to think about, the machine learning pipelines, let's generalize those. Let's assume they are like set of tasks, and there is this dependency on this task. So one needs to happen before the other. And then some of those run in Spark, especially the ones that are in the beginning, and then some of them would need to run using Python, but they are preferably in the later stages when you train the model or do reports and other stuff. But what we see is that as we scale out from pilot stage to industrial scale, or from industrial scale to globe scale, then we see that the number of scenarios increases. Now, what is a scenario? So one way to interpret the scenario is that each run of a machine learning pipeline can be characterized by some kind of a location information, some kind of a time span information, and product information. And product in this case, let's say garments. To give you a bit more example, let's say we are trying to figure out the discount prices for products that are sold online. In this case, location information would be like one location would be Sweden, and time span could be winter, and product could be, let's say, a bunch of garment that explains winter wear. Now, this is one scenario. There are many other scenarios to run. Not only we want to run in Sweden, we also want to run in other Nordic countries, other European countries, in any other countries in the world where we have the footprint. And then not only we want to run it for winter, maybe we want to break down winter into 2 seasons. So early winter before Christmas and after Christmas, or think about any way to break down the time. And then we are not just selling winter wear, we are selling all types of garments. So basically, as we scale up more and more in our business, we have to run these ML jobs manifold. And depending on the size of the market, depending on the period and the batch size for the product, the execution time can vary quite a lot. Some would run very, very fast. Let's say we are new entry in a market. So therefore, I would assume that the demand is quite low there. On the other hand, if we are in an established market, let's say Germany, then the demand is quite high, and then we have to deal with a much larger batch of articles or garments. So basically what I'm trying to say is that we have to deal with many runs in parallel because we are operating on all these markets at the same time, at the same period. But it doesn't mean that all of these runs has the same type of requirements. They vary. Now, before we talk more about the scale, let's look at what do we need to run this job effectively, any single job. So the first thing that we need is that because there are many scenarios and we don't want to create these scenarios manually, we want to create a schema, and then we inject the config parameters that would basically expand the schema dynamically, populating the scenarios. And we see that Airflow is a very good tool to achieve that. So you define a DAG, which is basically your task graph. You define a dependency on these tasks using a specific syntax. And then you inject external parameters to populate this schema using different scenarios. And then on top of it, you want to schedule these jobs, meaning that you want to run this job at a certain point in time. Maybe you want to run them manually, when everything is ready, but that's not always the case. Most of the time, there are like scheduled jobs that run. And then you also want to monitor these jobs, meaning that are they running correctly? Do you need to intervene? What's happening how long is it taking now? So and then you want to track progress. You want to, if they fail, you want to observe the issues in the log. And then from time to time, let's say you intervene, you fix something, you change something, you want to start, stop, and restart this task. And we see that Airflow, out of many tools that are available around, all around the world, Airflow is one of the best tool for this job. It has its limitations, but it is good enough to do all the things that we need to do. Now, in terms of scaling, Airflow doesn't give you a scale. The scale comes from like, how do you increase the number of amount of compute resource up and down as your number of runs increase or decreases. And we see that Azure Kubernetes service is the perfect tooling for it. The reason why I would mention Azure Kubernetes service is that H&M currently is in a partnership with Azure. That means all our services, we run natively in Azure public cloud services. Now, so we need a Kubernetes service. We are using Azure Kubernetes service. And what it would do is that it would basically allow VMs in VMs to be large VMs to be hosted as clusters. And then it would allow us to basically create pods that host Docker containers to run different type of jobs. So, and therefore, we basically are looking for some way to use Azure Kubernetes Service so that we can allocate the compute resources to these jobs, and by that extent to the tasks dynamically. If we have a lot of tasks, we want to spin up more pods. If we don't, then we want to reduce those number of pods. And then we want some fault tolerance. If they fail, there should be a way to bring up that task again. And of course, we also want to isolate this context. We want to run these jobs across many different use cases. We want to run these jobs in different settings, maybe in production setting, in testing setting. So this is important as well. And Azure Kubernetes Service provides all of this to us. Now, the interesting thing is that we need Airflow, we need Azure Kubernetes Service, and we also need dependency injection, meaning that how do you inject the source code, the DAG, the config to these tasks. We also need data integration, because all of these is meaningless if you cannot connect to the data. So how do we connect to the data? Then we need model management. We need to train model, then we need to track those model. We need to test those model, then we need to serve those model. What is our model management platform, and how do we integrate those? And then we also need a way to debug the errors. And it's not just debugging the runtime errors, it's also debugging the errors that might show up in the infrastructure. Maybe the Airflow scheduler is not working correctly. How do we fix that issue? Maybe some jobs are stuck. How do we get them up and running? And then finally, what kind of development environment do we want to provide? Because not only we want to run them in production, but we want to adopt them as the time changes to meet the new demand, to make new decisions. And then what kind of developer support we want to provide in this setup. Now, I'm not going to give you answer to all of this, but I'm going to, because we don't have enough time, but I will show you some high-level overview on some of these aspects. So how do we implement this scalable ML platform? So the first thing we do is that we integrate Airflow and Azure Kubernetes Service. And the way we do it is that we want to run the Airflow services, the core Airflow services like the scheduler and the web UI in a separate cluster, in a separate namespace. And this cluster footprint does not have to be, this cluster, the compute resource in this cluster does not have to be big, because these jobs are basically controlling jobs. And then the schedule, the Airflow components also need some kind of access to the data where we maintain the DAG databases. However, the place where the actual computation runs, meaning that Airflow workers. These Airflow workers are hosted in another cluster. And then the way we do it, a DAG, which is a set of tasks, each task run in a separate container in an isolated pod. The benefit that we get out of it is that you can actually inject the right compute resource to each of these jobs separately, meaning that you can, because if you think about it, in the first job, which runs in Spark in a Databricks managed cluster, your pod do not execute anything. It just communicates with the Databricks cluster. And therefore, it can be small. On the other hand, if we go here we will, let's say we are computing, we are training a model, and then we need a very large machine. But if the market is small, you can inject a smaller machine compared to this one, for example. So this isolation of compute resources for task allows us to basically apply the right size of compute resource to the right task. And then we understand that maybe one VM to host this cluster may not be enough. And we exploit the benefit of Azure Kubernetes service, which can increase this number of nodes as high as possible that are available through Azure Kubernetes service. So if you have a lot of scenarios running, it would start with one node, but over time it can expand up to 4 or 8, for example. And if we see that the load is even higher, that goes beyond the capacity of Azure Kubernetes service, beyond one cluster, then we can, for load balancing purposes, we can host several clusters. Right. And to paint the picture a bit more clearly, we maintain all data in Azure Data Lake. So that's where all the DAG, all the run data are stored and read. And then we manage all the models using MLflow. I mean, this is a new area, model management, that is emerging every year now. And we have seen that MLflow is if not a clear winner, it is a dominant force in the ecosystem. One thing that I forgot to mention, but I would like to iterate again, is that one key aspect of our choosing the technology is that we want to choose something that is backed by open source community, because we see the power of the wisdom of the crowd has a lot of value in choosing the right technology. However, that doesn't mean we will use the open source solution to host it ourselves from the very beginning, because we want to roll things out in production as fast as possible. Once we see that with the managed services, we cannot achieve that scale, then we think about, can we design something that would allow us to scale even better? Last thing is that the dependency, the source code and the DAG and the config. So we manage those currently using Azure file shares. So, and that's why you see that this component, the Airflow component, has connection to Azure file share, which basically reads the DAGs. On the other hand, there is some connection between the tasks and Azure file share because they use the source codes. Now, one aspect, one big challenge that we had to address was, how do we achieve statelessness when we are running many different scenarios? What I'm trying to say here is that, how do you run different DAGs in the same environment? How do you run different source codes in the same environment? What I'm trying to say here is that maybe this run is based on a specific DAG and a specific version of the source code, and this run is for another DAG for another version of the source code, and the same argument goes here. And the way we do it is that we have basically designed it in such a way that this DAG would, without going too much technical detail here, is that the green basically means it looks for specific state that would resemble the green state. And that would reflect in the Azure file shares, that would reflect in the DAG in Azure file shares, the data in Azure Data Lake, and the source code in Azure file shares, and also the tracked run in MLflow. And then no matter in which state you are, you should be able to pick the red state or blue state whenever you want to. So this is on a design level. So basically, how do we implement in these Airflow DAGs? I mean, there are a lot of details that we can go for, but something to explain on a high level is that we use basically appropriate size pods. We select specific type of compute resource that is appropriate for the task. We use different types of Python operator, but we are we want to keep it to a low number. So right now we are using Python operator for all jobs that could be run using Python. Certain system command we also run using Python operator, just to keep it simple and keep it flexible. For integration with Databricks, we use Databricks submit operator. And then we don't want to run, previously I told you, like when we design this DAG, we also want to run it in test environment. That means for the same DAG, we have a production version, we have the test version, and different types of test version. But we are not going to implement different DAGs for it. So what we do is that we use branch Python operator to choose the right type of run. And then we also want to decouple ML-related source code from the DAG. What we mean is that the DAGs are loaded long before the actual run happen. So therefore, if we change the source code, we don't want to change the DAG. So therefore, we have some kind of a proxy solution that would load the source code in the runtime. What the DAG does is that, so anytime you define a DAG, in every task, you have to define what function to run, and that's called Python callable. And then this Python callable, instead of pointing to the actual task function or actual ML function, it points to a proxy function that would load the actual function during the runtime. We also have put some effort into increasing the observability in the system. Basically, that goes to the theme of debugging errors. And so what we are doing is that, so we are hosting a Jupyter Hub in the same cluster, in the same namespace where we are running the DAGs. That allows us to load certain run using its own source code, using its own data, using its own state. We also have, we also use Azure Insight to look into the health of the, to query the log to understand the health of the scheduler and the web UI and other critical job components. Right, so the question is, how do they fit together? So basically, we have on a high level, we have two types of run. So we have either production runs, which you see in the bottom. So we have some kind of a scheduler. It's an application that would schedule this job that interacts with, that is accessible to our business. They schedule this job, they trigger the job to our cluster manager, which is Azure Kubernetes service, which triggers the job to our job manager, which is basically Airflow, which basically schedules the task which runs in Docker or Databricks Spark cluster. And then finally, these tasks would do some kind of a model activity, which runs in Airflow. But we use the same setup for our continuous integration run, meaning the development feedback. So, and there we have a bit more involved process. So of course, we don't want to do any model activity during the continuous integration. We want to run backtest, which is similar to these steps. But before that, we do other stuff. For example, we build we perform build operations like creating a new image if there is necessary, testing the code health, for example, like running unit test or static code analysis. And so these are the different systems that we use in different aspect of the model lifecycle. If we go through this whole list, it will take me quite a while. For the schedule, let's I look forward to some questions that you have. And finally, so what is our future? So basically, the system that you see here is reflection of the current moment, and it will change as the technology upgrades, as new challenges emerges. We are adapting, and to do that, we look into we want to use the best technology out there that is risk averse, meaning that is stable. We also want to choose something that does not locks in to a specific vendor. We still want to keep it to some level vendor neutral. So going for Python, going for Airflow, going for Kubernetes service, going for MLflow is inspired by that choice. But none of it would be possible without having talented people in the team. We don't have hundreds of engineers working on this. We are few people supporting a lot of projects, and we do this because we feel that we will do anything that we can do for the best of our customers. So I present you here one of our CEOs that scaled H&M to the Europe and to the world. And right now we are in the next stages, and we are looking forward to have more talented people to design awesome solutions in the coming year. Thank you.
Thank you, Misbah, for such amazing presentation. Now we have question from the audience. So the audience asks, what do you think is the most challenging part of the ML pipeline?
So designing a pipeline is not that hard. There are a lot of good algorithms out there. There are a lot of good source codes that we can readily use. There are two problems that we see. One is that when we choose this pipeline, when we use the data, how do we clean the data in the best way possible so that this ML pipelines gives us the best result? The other thing is that we have a history. We are not working on this from scratch, and it needs to work in production. We need to improve things. That doesn't mean we need to stop doing what we are doing. What I'm trying to say is that if we want to change X technology with Y technology, X system with Y system, we cannot stop the X system. So the challenge becomes like it's a running train which is going on X engine. Now, while it is keep running, we need to switch to the Y system, and that's where the engineering excellence comes in. Like, how do you change the engine of a running train, no matter it is slow or fast?
Thank you. And probably the last question from our audience. So another audience asks, how big is the team that work on this pipeline?
So our teams vary depending on the size of the project. So we may have 5 people team to 20 people team, but it's not just engineers. We have product owners, we have data analysts, we have data scientists, and we have software engineers, DevOps engineers. But there are probably no more than for each role 1 to 2 person in a team. And the way we solve this problem is that not only we look into our team how to solve this problem, we also reach out to the other team, whoever is an expert in Azure Kubernetes service or Airflow or model training or on a certain algorithm. We reach out, we collaborate. So we basically try to find creative ways to enhance our capability.
Thank you, Misbah. This is the end of this talk, and please follow up with the next one on 2:15. It should be 1:30. Thank you.
Thank you. It was a